Well, good morning, dear, and welcome back. And you have started watching video on support vector machine. Today, we are going to discuss very interesting topic within support vector machine, rather continuation of what we discussed earlier. This is regularization, and the basic concept is very simple, or its other name is soft margin support vector machine. The basic concept is this. You see, suppose we have two classes. These are my features, S1, S2, and these are my samples. Now, what if samples from this class is approaching towards sample of this class? Means, you see, this is encroaching. This is called outlier. This should not have been here. It should have been here. Similarly, it could be here also. Okay. So, if that is the case, then we are trying to test support vector machine how robust it is. Okay. And that robustness we are creating by adding a regularizer term. Okay. Its very concept is simple. So, we have attached a parameter regularizer C, and we have assumed that for any arbitrary outlier, the distance from the appropriate class support vector line is zeta I. Okay. So, from the garter actually. So, this outlier from this own garter is deviated, and the distance is zeta I. Okay. And then we are just this is our objective function. Objective function is to minimize half, that is parameter W square, and we are adding this regularizer term, and then zeta I, sample I equal to 1 to m, and the role of C here, you see, that means what we are trying to do through this C, we are trying to figure out that it should be, although this guy is there, zeta I is here, its job is to still keep half W square small, and to ensure that most of the sample have functional margin at least 1. That means it should be here. Functional margin should be 1. Okay. So what we have done, just modified an objective function. This is, you can also call penalty. We have added a penalty term that if there are outliers, then we will penalize it. Okay. And then constraint also. So, this was our earlier constraint, yi times, you can recall that w dot s I plus b plus zeta I. So, we have added zeta I here also, and that was the constraint greater than equals to 1 for all the samples. And then we are just simplifying it, taking zeta this side, it became 1 minus zeta, and zeta also has to be greater than equal to 0. Okay. So, this is my objective function now, changed objective function with regularizer, and this is my changed constraint with that outlier associated distance associated term. Okay. And then we are trying to formulate Lagrangian function. Now it is a function of W, B, zeta, alpha, beta. So, as many inequalities are there, we will have to add that many these Lagrangian multipliers, what we have done here. Okay. So, this is the rule, and that is the convex optimization rule, you know. And so, this is my objective function. This and this is my new objective function. Okay. And then we have added Lagrangian multiplier alpha I for this constraint, then minus another Lagrangian multiplier, bunch of Lagrangian multiplier beta I with this constraint, that is zeta I greater than equal to 0. Okay. Clear? And here is the figure. Okay. So, then like earlier, we can just solve the primal problem. How? by partially differentiating this Lagrangian function with respect to w and b and making them to 0, and then whatever value we got of w, we are substituting back and simplifying, and whatever we got that relation, that something equal to 0, you know, that b is giving that derivative of L with respect to b is giving that condition. So putting all of them, we are actually formulating the dual problem. So what is new here? You see, it is just, this is the dual problem, just like earlier. Okay, problem, the dual problem, there is no change, but subject to the constraint. Constraint, earlier it was 0 less than equal to alpha I. Now alpha I, that is a Lagrangian multiplier, is in between 0 and c. There is a regularizer constant. Okay, and as usual, I equals to 1 to m, alpha sub I, y prefix I equals to 0. So these are the constraint we have. So this is only new thing is here. Okay, this is only new thing. Okay, so once we have formulated this problem, and this is my w, you can see the nature of the w. Okay, so w is a quadratic function because alpha I, alpha j is there. So this is alpha squared. Okay, alpha. So this is a great quadratic function. So now we need to solve this function. Okay, so this is our objective here, and once we solve it, solve means what? This finding alpha. Okay, because you see, alpha is primarily needed, otherwise I cannot find w. W is also in terms of alpha. Okay, so essentially this is the training method. Okay, we need to train the support vector machine. Okay, so this is the training process, and once we know alpha, okay, then we can predict. Once alpha is known, the machine is trained. Okay, that means the parameters are known, that is w, b, those parameters are known, alpha is known. Okay, and then we can use that machine for prediction. For any new sample, plug in to that machine, and we will discuss that. If it is greater than or equal to 0, so this is our in the first class decision rule. Okay, greater than or equal to 0, then the sample belongs to positive class, less than 0 belongs to negative class. Okay. So I told you at the beginning that support vector machine is an analytical tool. Now we are deviating from here. So up to dual primal problem is fine, but dual problem we formulated, and you know why we formulated dual problem? Because training using primal problem solution is extremely difficult. That means designing algorithm with primal problem alone is extremely difficult. That's why we made a dual problem, and that we discussed actually. Okay, and here the dual and primal problem, their nature is same. Okay, so that's why KKT conditions and all have to be satisfied, because we'll move back and forth. Okay, so for example, we'll train support vector machine. Training means we'll figure out alpha, and then we'll go back to the primal problem. There we'll figure out w, putting this alpha value which we obtained from dual problem. So this is the thing which we are going to do. So we told that is an analytical tool, but now we are deviating, because for training we need again algorithm which will work on iterative method. Okay, let us see. Okay, there is one algorithm called coordinate ascent algorithm. Okay, consider our objective is actually, this is w is w is that function. This is not our parameter w. Okay, this is not. Okay, so you know, so this is another we just commonly named W, it has nothing to do with parameter, is a function. And the nature of the function is quadratic. But here, say, is the function of alpha 1, alpha 2, say alpha m. Okay? And we need to maximize this function over alpha. Now, coordinate ascent algorithm works like that. It takes, say, I have m number of alpha, m may be 1000, and then it takes only one parameter, alpha parameter, at a time. Okay, and it optimizes W, making all other parameters constant or fixed. Then if the optimization is done, then we take that alpha value by argmax function, we take it and then we keep it constant. Then take alpha 2 and making all other are constant, and again re-optimize W. And this is the way algorithm actually works. Let us see. Repeat till convergence for I equals to 1 to m. So this is the inner loop actually. So this Lagrangian, this is not Lagrangian multiplier. Let us say parameter alpha I assigned value of the function argmax, which is maximized over alpha I. This is the optimized value of alpha I. Okay, say W alpha 1, alpha 2. This is alpha I cap alpha I plus 1. This is the way we have written it. So I told you that how to optimize it. Is it clear to all of you? Because you see, we know this is a function. W is a function of, so say, okay. So I will keep this to avoid confusion with parameter W. So if you see, this is a quadratic function, right? Because we have alpha square. This is constant for a level. Okay, these are my samples. Okay, once they are given, this is the dot product. Okay, the samples. So everything is other than this alpha. Everything is known once the training samples are given with the level. Okay, so this is actually A alpha square plus B alpha plus C. This is of this nature, and we love such functions, right? Say now this is your W alpha, and this is your say alpha. So nature of the function will be like this, and we can run gradient descent algorithm so that I can reach to the minimum. If I need to minimize this, if I need to maximize this, of course, you know, the other way around. Okay, so this is W, and now we'll be having a function like this. Parabola. Okay, so we'll have to slowly we'll have to make a step, so that that's why it is called coordinate ascent algorithm. Okay, because if you see the nature of the function here, okay, this is of this shape. Okay, so we need to maximize whatever is the optimization, right? And it is known to you. So we have beautiful W, which is a quadratic function, and then we have an algorithm, coordinate ascent algorithm, and let us see minutely how it works. So say at a time I have taken alpha 1, alpha 2, I have m number, any two. Okay, it need not be first and second, any two, but suppose we have taken alpha 1, alpha 2. And what is this? This is the contour, since the quadratic function. So this function will have a contour. Okay. Okay. So if you have 2 alpha means contour, this is of this shape. Okay. Sorry, but you know. Okay, I think this is recapitulation from your gradient descent algorithm. So these are the contour. Okay, contour of that quadratic function. Now say start from any whimsical value of alpha. Here we have started say with this value, and look, you are when you are actually making a progress in the alpha 2 direction, alpha 1 is constant. So at a time only alpha 2 is varying. So repeatedly you are calculating the value of W and seeing it is coordinate ascent, right, and seeing whether W value is increasing or not, okay, increasing or not. So it is increasing until some value is reached that it is not increasing any appreciably, and then you hold it, and then go on increasing alpha 1 but making alpha 2 at that time constant. Then whatever possible you do that re-optimization, and then again repeat the same thing, that is make progression alpha 2 keeping alpha 1 constant, alpha 1 making alpha 2 constant, like that till you reach to the global optima point, that is at the top, okay, at the top of the bowl, okay, this is the global optimum point. So, and you are with this argmax function, you are just tracking those alphas which are maximizing this function W. Is it clear? So you have two loops here, outer loop and this inner loop. Okay, this is the inner loop. So in the inner loop, actually, you are optimizing, you are calculating the value of W, which is a quadratic function, and collecting those optimal alpha by this argmax function. Now this is a great algorithm, simple to implement, but it works well actually if W is such that argmax in the inner loop can perform efficiently, okay, then only this algorithm will work efficiently. Now, so this is the basic this coordinate ascent algorithm, I think, is clearly understood by all of you. It is progressing or incrementing value one at a time, okay. Just we gave an example with any two, okay. If there are hundreds, fine, one at a time, keeping 99 constant, then taking another one, only one, other will be constant, like that, okay. So this is a little bit computationally, it takes long, but it works. But can we, now let us ask question that can we use it for our training our support vector machine? The answer we will try to give you, just hold on. Say the answer is, for the time being, the answer is no, and why we will just show you. We cannot use the coordinate ascent algorithm as it is, because for our case there is a constraint, this is a constraint which we need to obey always, okay. And say it's very simple, if okay, so if actually this is a constant alpha I sub I equals to 1 to m equal to 0. So it's very simple. Say for a level alpha 1, y1 plus I equals to 2 to m alpha I yi equal to 0. So this is constant, right? You can call it zeta value. So we will prove very easily, and you will see that since we have this constraint here, although coordinate ascent algorithm is great concept, it cannot work in our case. So there are actually many training algorithms, but the one which we will discuss, which is a extension of coordinate ascent algorithm, is called sequential minimal optimization algorithm, or SMO algorithm, quite famous algorithm. Actually, it was developed by John Platt. It's known as the paper you can read, technical report. I suggest that you should read, and I will give you that. Sequential minimal optimization, a first algorithm for training support vector machine. So in 1998, in Microsoft Research, in the form of a technical report, he developed this algorithm, and which is one of the state-of-the-art algorithm for training support vector machine. We are going to discuss the basic essence of this algorithm in little details, because you will love this algorithm, because without that you cannot train whatever mathematics you have studied, although simple, but those will not be effective unless you know this algorithm. Then only those mathematics will speak, and you will know how important they are. Okay. So you see, just a little bit recapitulation. We have a KKT complementarity condition, which is given by this. Earlier, you know, this you have seen, right, in the primal problem itself, that this was my constraint, isn't it? And we multiplied it by alpha, the Lagrangian multiplier, okay, and that has to be actually 0, because when we are formulating alpha, which is minus, you have this, okay, times gi. This is star means optimal value. Now this is called KKT complementarity condition. This is a very beautiful condition which tells you something. What is it? You see, the product of two quantity is equals to 0. That means when alpha is our Lagrangian multipliers. If alpha equal to 0, that means when product of two quantities is 0, either of this will be 0, and that will satisfy this constraint, right? Of course, both of them could be 0, but here it will not happen like that. So important thing is either of them is 0, will be this constraint will be satisfied. Now let us see, if alpha equal to 0, then this cannot be 0. So this will be greater than equals to 1. Okay, so this is one constraint. Very useful constraint for checking the convergence of the SMO algorithm. That's why we are writing it here. And then you have seen that soft margin support vector machine, alpha is lying between 0 and c. So alpha I, if it is equals to c, then this less than equal to 1. Okay, and in between, if it is lying between 0 and c, then is equals to 1. So these are the three very important convergence criteria that called KKT dual this is called KKT dual complementarity condition, which will be useful for us for checking the convergence of SMO algorithm. So in the next class, we'll start from here, and that eventually, if we just see that this tells you that out of so many, now you know that if we have 1,000 samples, and I do not know who are the support vectors, so we attach alpha I to all the samples. Okay, every samples I equals to 1 to 1,000, the alpha I will be attached. However, when we are trying to evaluate alpha I, you will see that alpha I will be 0 for most of the samples, except this is equals to 1, isn't it? So if alpha is not equal to 0, then this will be 0. That means this constant, this is equals to 1. Okay. So that means, most of the cases you will see other than the samples on the gutter, the alphas will be 0. So we'll start from here. So it's not that difficult to train a support vector machine, because mostly the alphas will be 0, because out of 1000 samples there will be very few support vectors. And how to know that they are support vectors? For them, alpha will not be equal to 0. Okay. And for others, alpha will be 0. We are getting from the complementarity condition. Well, thank you very much for your attention, and we'll continue from here, and we'll throw some light on how the sequential minimal optimization algorithm works to train a support vector machine. Have a nice day. Stay safe. Bye-bye.